Hi, in this lecture we are going to start going over the backpropagation calculus and maths. Our goal over the next few lectures is to provide an underlying mathematical theory behind the process of backpropagation. I just want to note that things might start looking progressively more and more complicated, but don't worry, and I strongly suggest you take your time to look through all the slides to make sure you understand all these concepts. What backpropagation attempts to do is determine the sensitivity of the cost function to the change of each individual weights. Each weight can then be adjusted in proportion to its impact on the cost in the direction in which cost is reduced. The gradient of the cost function is equal to the average of the gradient of all the cost functions of each individual sample. Therefore, what we need to do is calculate the gradient of the cost function at each individual sample of trading data. The overall gradient, by which the weight will need to be adjusted, will be the average of each sample's gradient. Here we will just go over the definitions and notations one more time. And I do suggest you take your time to familiarize yourself with all the different notations we are going to use. And if you ever get confused further on in the lectures, you can always refer back to this slide. To start going through backpropagation, let us use the example of a super simple network with a single neuron per layer. This network has 3 weights and 3 biases, and we will use the sigmoid function as an activation function. So over this lecture, we are actually going to go through the maths behind backpropagation for this very simple network. Our goal in this lecture will be to calculate how sensitive the cost function is to each weights and biases in this neural network. So let's start by only taking a look at the last layer. We can see that the output of the last layer is equal to the sum of the inputs, and that through the activation function. And we will use Z as the term which represents the inputs into the final neuron. So Z would be equal to, in this case, W3 times A2 plus B3. And therefore, we can summarize the output of the final neuron as equal to Z3 through the activation function. By replacing our numerical index with the generic index L, we can quickly come out with these formulas below, and this will allow us to determine the outputs at all the other neurons. Now, to carry on forward, I will start by reminding you that what we are trying to do is we are trying to find the derivative of the cost function with respect to the weights and biases. Looking at what we got in the previous lecture, we can see that the cost function is a function of AL is a function of ZL, and ZL is a function of WL and BL. Therefore, we can apply the chain rule to calculate the partial derivatives dc over dWL and dc over dBL, so to get the partial derivatives of the cost function with respect to the weights and biases. By applying the chain rule below, we can see that we can calculate the derivatives with respect to the weights and biases by multiplying many functions that are easier to derive. However, we can apply the same principle to find the partial derivatives of AL minus 1 with respect to C. Carrying on forward, it is clear that the cost function can be expressed as a series of nested functions. In the illustration here, we can actually see the series of nested functions. So the function starts on the right with the cost function, which is a function of Y and AL. AL is a function of ZL, and ZL is a function of BL, AL minus 1, and WL. And AL minus 1 is a function of ZL minus 1, and this goes all the way back to the start of the network. So you can start to see where backpropagation comes in. To calculate the partial derivatives with respect to each weights and biases, you need to calculate the partial derivatives of each nested function and multiply them by each other. As the nested functions starts from the end of the network and carries on backwards, the process is therefore called backpropagation. Now, we are going to apply the chain rule to calculate the partial derivatives of all the nested functions. So again, we will start with the cost function at the end and work our way back through the network. So we will start by deriving the cost function with respect to AL, and that will be equal to AL minus Y. And then we would calculate the derivative of AL with respect to ZL, and that would be ZL1 minus ZL. This is because we use the sigmoid function as an activation function. And then we will carry on backwards to calculate the derivative of ZL with respect to BL, AL minus 1, and WL. And we will carry on forth all the way back to the start of the network. We can see that doing this by hand for every node is cumbersome. And to simplify the process, we are going to define a term delta L, which is equal to the derivative of the cost function with respect to ZL for every neuron. So the delta L in backpropagation is often referred to as the error term. So we are going to calculate this term delta L for every single neuron. And if we calculate all the delta L terms, we can easily determine the partial derivative with respect to the weights. So at each node or neuron, we need to determine the delta L values. And this value will allow us to rapidly computate the derivative with respect to the weights and biases at that node. Let us start with the last neuron, the output neuron. Well, delta L is equal to the derivative of the cost function with respect to ZL. And by applying the chain rule, we come to the conclusion that delta L is equal to the derivative of the activation function at ZL times AL minus Y. Now we are going to calculate the delta term for the previous neuron, so at delta L minus 1. Again, just like before, we want to find that is equal to the derivative of the cost function with respect to ZL minus 1. We apply the chain rule, and then we find that would be equal to the derivative of the activation function at ZL minus 1 times the weight, WL, times delta L. So we can see that we can figure out delta L minus 1 from delta L. So delta L represents the derivative of the cost function with regards to ZL at the neuron. However, this can intuitively thought of as starting with an error at the output layer and backpropagating backwards to calculate the error at each node and using that to adjust the weights and biases. This is an intuitive framework that a lot of people use, despite it not being mathematically rigorous. In summary, let's go over the entire backpropagation algorithm. Well, calculating the delta terms of each neuron allows us to quickly figure out the partial derivatives. The process of backpropagation revolves around the calculation of the delta terms. We can see that the process of calculating delta is like starting with an error term and propagating backwards through the network. So by looking at the actual functions, we can see that the first step is we need the error at the output to calculate the delta L term at the output. Then we need that delta L to calculate the previous delta L minus 1. And then we can use that to calculate the previous delta L minus 2. Once all of the delta terms are calculated, we can calculate the partial derivatives of the weights. Once all the delta terms are calculated, we can calculate the partial derivatives of the weights. We can do this by applying the chain rule at each node. So for instance, the derivative of the cost function with respect to the weights would be equal to the delta L term times AL minus 1, which is the output of the previous node. And similarly, the derivative of the cost function with respect to the bias will simply be equal to the delta L term.